Good morning, everyone. So today, let's keep working on a LeetCode quiz. Let's get a random question. Okay, this is a medium difficulty level difficulty question. So the question is, furthest building you can reach. You are given an integer array hats representing the hats of buildings, some bricks, and some ladders. You start your journey from building 0 and move to the next building by possibly use bricks or ladders. By moving from building I to building I plus I, 1, 0 indexed. If the current building's height is greater than or equal to the next building's height, you do not need a ladder or bricks. If the current building's height is less than the next building's height, you can either use one ladder or hi plus 1 minus hi bricks. Return the furthest building index, 0 indexed. You can reach if you use the given ladders and bricks optimally. Interesting. This is the first time I find LeetCode has a GIF rather than static image as an example. Okay, so here are 3 examples. The first example, the heights are 47, 6, 9, 14, 12. Bricks is 4. Ladders are 1. Okay, so starting at building 0. Firstly, go to building 1 without using ladders, no bricks, since 4 larger than 2. Go to building 2, use 4 bricks. You must use either bricks or ladders because 2 smaller than 7. Go to building 3 without using ladders or bricks, since 7 larger than 6. Go to buildings, use your only ladder. You must either use either bricks or ladders because 6 smaller than 9. It is impossible to go beyond building 4 because you do not have more bricks or ladders. So, okay. Okay, so the second third example, yeah, it doesn't give the explanation here. Okay, I have some thoughts. I think that the bottleneck is how to utilize the ladder, right? So let's think about test case first. Firstly, let's get some input. So let's say the building is 1, 5, 10, 20, okay? And let's say we have bricks 10. We have ladders 1, okay? So step 0. We start at index 0, right? We need to have remaining bricks as, let's say, 10. And That's to say how many heaps we need. And what do we need to do? We need to move from 0 to 1. Correct? Then the clamp we need to do is 4, right? Actually, we need to think about, okay, should we use 4 to, we use ladder or bricks, right? This is something we need to think about. So what should we do? We should push 4 into the minimum heap. So then what happened? Then the minimum heap will become 4. And and the heap size is 1, right? Then it's smaller or equal the ladder's size, because the ladders at this moment is 1. Correct? Right? So bricks remainings here 10, because we use nothing. Okay? And then what do we need to do? We need to move from 1 to 2. Right? If we move 1 to 2, how many we need to clamp? We need to clamp 5. And then again, let's push 5 into minimum heap. And now the minimum heap will be what? We have 2 elements, 1, 5. And the heap size, now heap size is 2, right? And it's larger than the ladders we have. So what should we do? We should pop out the smallest heap, right? And pay with bricks. Make sense? Because because the bottleneck is heap, so we always start from ladder. Okay, since we need to pay bricks, so now our bricks remaining will be what? Will be 6. Make sense? And again, our heap will go to, will drop down to 1 element, which is 5. Let's keep going. We move from 2 to 3. How many we need to climb? We need to climb 10. And again, we put it in the heap, right? So we push 10 into minimum heap. And now what? The minimum heap is 510. Makes sense. And the minimum size is 2. Again, it's larger than the ladders we have. So what do we need to do? We need to prompt the smallest. With smallest, 5 is smallest, right? And pay with bricks. So what happened now? Now the heap, the bricks remaining will become 1. Okay? And the minimum heap will become what? Will become 10. And then we find that, okay, end of the building. We need them to do this again. Then just return 3. Make sense? Yeah, I think that this this question is pretty this requirement is pretty straightforward, and the strategy we use here doesn't use any tricky operation like bitwise operation or any tricky data structure or algorithms. So the input, 3 inputs. The first one is heights, list int. Second one is breaks, int. Third one is lighters, int. And we need to return int. Okay, good. So again, we need to initialize a heap with empty list. And then the index 0. And we need to know the length of the heights. N, make sense? Then what we need to do? We need to iterate, right? We iterate where there is a next building, right? As long as we have a next building, then we keep going. Okay, so as long as I smaller than n-1, we will keep going, okay? So let's do some initialization first. So the next height will be heights I plus 1. And the current height will be heights I. Clamp should be next height minus current height. Okay, make sense? Then what should we do? We should only consider positive clamps, right? Because if it's negative, that's great. We need neither lighters nor breaks. So if clamp larger than 0, we just push, right? Heap, push, right? So imagine a heap. The last element we will push the clamp into the heap. Okay, and then we need to compare the number of recorded clamps with the lighter, right? Compare recorded clamps with lighters. Well, then if len larger than lighters, right? This is a moment where we need to pay with breaks. So we need to prompt out the smallest clamp. So heap pop out, right? Remove the smallest. Okay. And then we need to do what? We need to pay with breaks. That makes sense, right? So breaks will be smallest clamp. Okay. Okay, then what do we do? We will stop until the breaks, we use up all the breaks, right? So if breaks become negative, so if breaks smaller than 0, what do? We just return I, because that's the furthest place we can reach, right? and then move to the next. Then return n minus 1. Sounds good? No, this should be yeah, I think this makes more sense. So I think that the main trick here is the operation of the no attribute head push. Okay, so we cannot use this library here. I'm not sure that import any makes sense, but I don't know, but let's see. Yeah, it seems that it doesn't allow me to import HipQ. Okay. I think that in the LeetCode, you cannot import certain modules. Correct? Module objects has no attribute. Head push. Oh, hip push. My bad. Okay. Oh, I can use hip push. Okay. So the runtime complexity is O n log L. And the memory is OL. That's good. I think that the main trick we want to review here is the operation on the heap. So explain the building functions, methods, or operations, and visualize a tester case step by step test case in the worst case for the code. Yeah, I think that, when I was a sophomore in undergraduate, we have this structure classes. And that's the very beginning I began to, to know the concept of those data structures like heap, linked list, whatever. At that moment, I actually didn't realize how important or what's the meaning of those data structures. But after I began, to solve these questions, I began realize how valuable this structure it is. So what's the learning here? The learning here is that, the best way to learn something, again, is still to use it first. You have a motivation, you want to solve a problem. And when during solve this problem, you find you need something. Then you begin to learn it. It will be much easier for you to remember those concepts rather than maybe remember those things before you start working on some stuff. Okay. So here's some, important operations here. Heap dot heap push. This one will insert X, keeping minimum heap in ascending order logically. Okay, so this is a binary minimum heap. Okay. So this is not just the keep X in, put the X in heap, but is heap in this ascending order. So on the top, on the entry of the heap, the element will be the smallest element. And heap pop, min heap, removes and returns the smallest item. When we have too many ladder claims, we reclaim the smallest one and pay it with bricks instead. Then min heap, numbers of times we currently assign to ladders. Okay. The other is straightforward. Okay. Again, here is an example. The input, we have 3 bricks, 2 ladders. Heap is nothing. Okay, and the heights is 1, 2, 3, 4, 5, 6, 8, 9, 8, 7, 8. Right? So when I is equal to 0, climb is 1. We put 1, we make heap is 1. Okay. I is equal to 1, we make heap is 2. I is equal to 2, we make heap is 3. And because we it's too big, then we need to pop 1 element. Now the remaining brick is 2, and the heap is 2. As equal to 3, again, we consume brick. Brick is 1, heap is 2. As equal to 4, heap is 3, brick is 0, heap is 2. I is 5, then brick is -1. Brick is smaller than 0, so we cannot go ahead. So we just return I is equal to 5. Okay? So just return 5. Okay. Okay. Yeah, I think that can you explain the Python library IQ, right? Because this is what we import at the very beginning. I guess, because AI can remember the library much, much better than humans. So they can utilize those library much better. So a heap is a special binary tree that satisfies the heap property. In a min heap, every parent is smaller than its children. Therefore, the root is always the smallest element. If store this battery, well, I shouldn't be specific. Can you visualize it? Right? And also that, again, humans is a pretty visualized animal. So if we want to get some explanation, use a visualized way is much, much better. Okay, so heap Q stands for heap Q, a Python library that implements a Min Heap using a plain Python list. Think of it as a priority box where you can throw numbers in any order, but when you pick or pop, you always get the smallest number first. That's why it's called a Min Heap. Internally, it's a binary tree stored in a list that always satisfies the heap invariant. For every all node at index I, its value is smaller than the value of the children at indexes 2 multiple I plus 1 and 2 multiple I plus 2. So here's a visual model. Let's say we push value 5381 into a heap. Okay, pew, 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 pew. Then the list looks like 1385. 1385. Okay. But conceptually, it's a binary tree. Okay. 1385. Okay, this is a breadth first, BFS. So the smallest element 1 is always on the root, which is index 0. That's why when we pop out, it will always pop out first, right? That's a heap property. Python doesn't store a tree object, just a list arranged in this structure implicitly. So for example, right, if you don't know binary tree, then when you say heap is at least 1385, you have no idea what does this hell mean. But when you understand it's actually stored in a binary tree, then it's super clear, right? Yeah. So when you heap push, Python will append the new element to the end, then bubbles up until the heap property is restored. When you heap pop, Python will remove the root, which is smallest element, then move the last element to the top, then bubbles down until the heap property is restored. Okay. Yeah, so here are some common operations. Heap push, push new elements. Heap pop, pop smallest elements. Heap push pop, push then pop smallest. AP5, convert list into heap in place. N smallest, return K smallest, N largest, return K largest. But it's interesting, you see, the sequence of the two parameters is different, right? Here, push and pop, heap is the first parameter, but here, N smallest or N largest, heap is the second parameter. Okay. Well, what's TLDR? I think it's some abbreviation, but I don't remember it very well. TDDR? TLDR? Too long, don't read. It starts as an internet snag, but it's now used formally to mean a short summary after no explanation, like a final takeaway or busy readers. Okay, good. Yeah, so imagine Heap Q as a smart to-do list sorted by smallest number. You can toss any new jobs at any time. The smallest priority number always jumps to the top. Each insertion remove keeps everything efficiently sorted, but only partially. It doesn't know the full sorted order, just the smallest one quickly. Okay. Yeah, I think that's a good quiz question because it helps us to review the operation in a smart heap. Okay, thank you everyone. Bye-bye.